Topic 5 of the ocean circulation, thermohaline circulation. So we have discussed the surface circulation up to this point, and the surface circulation only affects the uppermost layer of the world ocean, so about 10% of the volume, so everything above the picnic line. But most of the water is in the deep ocean. And there are horizontal and vertical currents that exist below the picnic line in the ocean's deep water. And this water is driven by density. Density is a function of temperature and salinity, and that's why we also call it the thermohaline circulation. The deep water circulation is much slower than the surface circulation. So the slow deep water circulation is driven by density differences and not by wind energy as the surface energy. We call it the thermohaline circulation because density is a function of temperature and salinity. T stands for thermo and S haline, so thermohaline circulation. And remember that cold water and more saline water is more dense, which you can see in the lower right image. So this is the classic model for the thermohaline circulation. So you can see that on the x-axis we have to the left the equatorial regions and we have to the right the polar regions. So the lower regions near the lower latitudes near the equator, they are heating up, and near the polar regions they are cooling. So we have this cold water near the polar waters is sinking because it is denser, because it's cold, than the warmer surface water. So in the polar regions, the water is sinking and then it's starting to spread. And you can also see that the surface water coming towards the polar region is warmed by the equator. So that sinking and that supply of warm water that's slowly cooling as it reaches the polar regions is driving the thermohaline circulation. So this is the classic model of pure thermohaline circulation. So in this picture, you can see a cross-section of the Atlantic Ocean. To the left, we have Antarctica, the south, and we're going all the way up to the North Pole. Remember that in the north, the Arctic Ocean is an ocean, not a landmass. And you can see that the ocean is density stratified. The surface water is the least dense water, so it is on the top. But then we have the intermediate water that is a little bit denser. We have the North Atlantic deep water, and the deepest water is the Atlantic bottom water. So NADW stands for North Atlantic deep water, and AABW is the Antarctic bottom water. The warm water, in red, has low nutrients, but it has a lot of oxygen because it is in communication with the atmosphere. And as we talked before, the atmospheric gases and the ocean surface water gases are calibrated, they're exchanged freely. And here in this picture you can also see that the deeper water has increased nutrients and also more carbon dioxide. When the water downwells near the poles, it removes a lot of CO2 from the atmosphere and stores it in the deep ocean. So this diagram is from your textbook, and it shows a simplified view of the thermohaline circulation in the Atlantic. And so what you can see is towards the top of the water, of the diagram, the surface water in red becomes denser and it sinks to the bottom. This is the North Atlantic deep water. And the Antarctic bottom water, which is in dark blue, is the densest water that we have, and it forms during the winter near the Antarctic. So today the formation of and the downwelling of deep water occurs in the deep water. So the thermohaline circulation affects all the ocean's water. The movement of water due to the different densities is the thermohaline circulation. The ocean is density stratified with the densest water at the bottom. And now we're going to be looking at the North Atlantic deep water and the Antarctic bottom water because they are forming via two different processes. Deep water forms in the polar regions, and there are two different processes. And we're going to be looking at the North Atlantic deep water first, the NADW, and then at the Antarctic bottom water, the AABW. So here in this diagram, you can see the surface currents in red and yellow, and the deep circulation in the blues and in the purples. So let's locate the Atlantic Ocean, which is towards the left of the diagram. And you can see the Gulf Stream in red crossing the North Atlantic. So here in this diagram, instead of showing the gyre, it shows the branch of the Gulf Stream and the North Atlantic current going into the Norwegian Sea and sinking. So the Gulf Stream water is very salty and warm, but as it crosses the North Atlantic and goes into the Norwegian Sea, it is starting to cool, but it still is very, very salty. In the Norwegian Sea, this water encounters the water coming from the Arctic, and the Arctic water is cold, but it's much fresher. And so now in the winter time, the water of the Gulf Stream is much denser than the fresh Arctic water because it has that big salt component, and the water starts to sink. And we have two places in the North Atlantic where this North Atlantic deep water forms, and they both are in the polar regions of the North Atlantic, and you can see them on the diagram indicated with the sinking. That water is now indicated in that purple water. That water flows back at the bottom of the Atlantic Ocean towards Antarctica. It is actually flowing in the opposite direction as the Gulf Stream water in the surface. But remember, the surface circulation is really, really slow, and it takes about 1,000 years for that water to reach Antarctica. And you can also see in the Antarctic water, there's also sinking taking place, and that is the Antarctic bottom water, and we're going to be talking about that in a minute. But what I want to point out is that these water masses that sink in the North Atlantic and around Antarctica are traveling to all the ocean basins. They travel into the Indian Ocean and also into the Pacific Ocean. The Pacific Ocean is that big ocean towards the right of the diagram. So the North Atlantic deep water is formed by that warm, salty water that is carried northward in the Gulf Stream and the North Atlantic Gyre. Some of that water enters the Norwegian Sea. Here that chilled, dense, salty water is denser than the fresh polar water and therefore sinks. So this is the formation of the North Atlantic deep water. The Antarctic bottom water forms differently. It forms primarily through brine formation during the Antarctic winter. So you can see on this diagram the Antarctic sea ice maximum during the Antarctic winter and the Antarctic sea ice minimum during the Antarctic summer. And because of that sea ice formation, we have Antarctic bottom water forming. So when sea ice forms, we talked about before when ice forms, how organized the crystal lattice gets. So when sea ice forms, it does not want to have that salt in its crystal structure, and it expels the salt. First, that salty water that's being expelled accumulates in these brine channels. You can see that in that diagram in these blue lines. So the top layer is the sea ice, and then the sea ice is pure fresh water. And below that you see the sea ice that still has a little bit of salt, and that salt is accumulating in these briny channels. And eventually these briny channels get so heavy, and by gravity that briny water drops to the seafloor. And because this water is so salty and so cold, it is the densest water mass that we have on the ocean floor. I added a video clip that was filmed by a BBC crew. They set up cameras for a documentary under the sea ice. And then for the first time, we saw these briny channels reaching the seafloor. And in the BBC movie, they called it brinesicles. And you can see that column of ice that is coming down. So make sure you watch that short video clip. It's just about 2 minutes before. And here you see again from BBC one of these pictures of these brinicles. So these brine channels are so super cooled that seawater along them freezes. And when they reach the seafloor, they kill anything in their pathway. So this picture you see a lot of brittle stars and sea urchins being flash frozen by the brinicle. So Antarctic bottom water is the densest water mass in the world. It is produced near the Antarctic coast during the winter months through brine formation. And it migrates long distances northward. It migrates into the Atlantic Ocean, into the Indian Ocean and Pacific Ocean. It takes about 1,000 years to reach the equator in the equatorial Pacific, and another years to reach the Aleutians. In the Atlantic Ocean, it takes about 750 years to reach 40 north. That's how far north the Antarctic bottom water reaches in the Atlantic, as you can see in the diagram to the left. And remember, the Antarctic bottom water is the dark blue. And before we finish this chapter, I have one quick concept check questions. So what water mass is the densest in the world? It is the Antarctic bottom water. The Antarctic bottom water, the most distinctive of the deep water masses, is characterized by a salinity of 34.7 0.65 per mil and a temperature of 0.5 degrees centigrade and a density of 1.079 grams per cubic centimeter. This water is noted for its extreme density, the densest in the world ocean, for the great amount of it is produced near the Antarctic coast, and for its ability to migrate along the seafloor north. So this concludes chapter 9.